Morning, everyone.
Good morning.
How are you guys doing this morning? Okay, so today I want to briefly finish what we were discussing last week. That was the dimensional analysis to help us simply as a way of do physics, explore new physics. And after that, we will switch on to talking about one-dimensional kinematics. So going back to this problem, the period of a pendulum, you all know what a pendulum is, right? You have a string and have an object attached to a string, and this object could just simply go back and forth, back and forth, back and forth. So that is a pendulum. So if I want to know what the period of the pendulum is, say the time it takes for it to go from the highest point and to the highest point on the other side and coming back to the highest point, that is one complete cycle, and that's called the time it takes is called the period. So how do we know? I mean, physics, obviously people have explored this doing experiment. For example, change the length, change the mass of the object it's attached to. But how could you figure out just by using dimensional analysis? Let's say you want to explore this and you say, I wanted to have an educated guess. What do? So you think about all the relevant quantities that might be enter into your expression. So you would be able to find the period, which we represent using time t, as a function of some other relevant quantities. So the length might matter, right? You make it longer or shorter. The mass of the pendulum bob, the object might matter. So you may have a mass. And it's possible when you put it on different areas on Earth, or if you move it up to the moon, right, with different gravitational strength, that might also matter. We will explain exactly what the little g is and later on in our kinematics course. But right now, let's just call it little g. That represents how strong the gravitational pull is at different places on Earth, or on Earth versus on the moon or elsewhere. So you think of all these quantities that might matter, and you say, okay, what if I just make this equal to that? They have to be equal. So each of them might be to a power of something, right? It may not necessarily be just the length. It may be length to the power of something. Let me actually, just to be consistent with my later slides, I'm gonna put the mass first. So I'm saying it's going to be the mass to the power of A, the length to the power of B, and the G to the power of C. So here I'm going to write everything using the dimensional analysis, saying, okay, the dimension of this is equal to the dimension of this, because you're setting them to the two sides of the equation, right? So it makes sense that they come out to be the same dimension. So all of those combinations better give you time. Otherwise, we know that we have made a mistake. So let's say you don't know anything, haven't done any experiment, you just simply want to find out. Okay, so the next step is simply plug in all the dimensions. So the dimensions for t is simply time. So you can use t here. And this is the dimension simply is just mass, right? So m here represent the variable mass that is also representing the dimension mass. So I'm going to say mass to the power of A. L is also the dimension of length. One thing we need to change is the little g, right? In terms of units, it's meters per second square. So what kind of dimension is that? Meter is a length quantity, so it's L. Second square is a time quantity, so that's t squared, right? So that's the dimension of g. But it's a g to the power of c, some unknown quantity. I don't know what the relationship is. So I'm going to say, so this is entirely to the power of c. And you have to set them to equal to each other. So now let's take a look. How can we make this equal? This is t. So, and this one does not have any mass. So how can we make this mass go away? We have to set a equals to which number? In order 0, very good. And I encourage you to all turn on your video if you can, and if you need to ask a question, feel free to stop me at any point. A has to be 0, so that m to the power of 0 will be 1. So you're not going to be affected by this mass. And you can see also it does not have L, but I have L to the power of B plus C, right? This is LB. This is going to be times LC. So LB times LC is LB plus C. But your left-hand side has no L, no length. So you need to make this to go away. You need to make B plus C equals to 0 again. You might wonder, okay, you have solved for A, but I don't know B or C. There's one last quantity, that is your time. On my left-hand side, I have time to the power of 1, right? And on my right-hand side, I have time to the power of what? So this is going to be MALB plus C divided by T to C. So on my right-hand side, I have T to the power of, so I need to set 1 equals which quantity right here? So this is T, 1 over T to the power of 2C. So it's T to the power of, is it 2C? Negative 2C? Is that right?
I think it would be, so sorry, maybe I'm misunderstanding. Is this like if you're moving it up to the top, or if you're trying to get it to equal 1?
Yeah, I'm trying to move it to the top. So it's T, this is T to the power of 1. So this is T to the power of negative 2C.
Yeah. Okay.
So once I represent everything in the same format, I know has to be 1 has equal to negative 2C. Does that step make sense? Okay, I'm seeing some nodding. For those who are not on camera, feel free to stop me if you want to ask more questions. Okay. All right, so I solved for my C. My C is negative 1/2, and which means I found my B. B would be 1/2 because B plus C has to be 0. So you see that you have found a relationship between time and these quantities. You should not have a mass in it, right? You can have a length in it, but the length is to a power of 1/2. It does relate to where you put your pendulum, on the moon or on Earth, and that is to the power of C, and C is 1/2. So to summarize, it's proportional to L over G and square root of that. Because G is negative 1/2, right? So G is on the denominator, L is on the numerator, and it's to the power of 1/2. I can just write it using the square root of L over G. You can see that this sign is like a little fish. This means it is proportional to. Meaning that this is not exactly equal to that. There's still some constants here. We don't know. Dimension analysis here get as far as getting the physics quantity in there, but it doesn't tell us the exact constant. That later on we do experiment, we'll find out we still need a 2 pi to make it exactly correct. But as far as our job at this stage, we're done, right? We have explored how the period of a pendulum relate to the length of the pendulum and the gravitational pull, the strength of the gravitational pull that you put your pendulum in. And that's entirely through dimensional analysis. We don't need to know much physics at all. We did not do any experiment. And this is the final result. I clean up everything and you have your solutions here on this page that we have already done. So that's an example of how physicists and scientists usually do physics, explore something that you didn't explore before, and then simply guess an answer. But it's better than a guess. It's an educated guess, right? It's not randomly plugging numbers. You are actually putting the 1/2, negative 1/2 there for a reason. So that briefly wraps up our discussion on dimensions and units. We will have plenty of opportunity to practice dimensions and units when we solve physics problems throughout our semester. So I wanted to start with next topic. Sorry, let me make this a little bigger. I think that's easier to see. Our very first topic is kinematics, right? This semester is about Newtonian mechanics. So we're looking at forces and motion and all of that, which is also very nice because it's related to our everyday life. It's more intuitive. So kinematics is the very first chapter, meaning that we'll study motion, right? And this week we will, first of all, develop some concepts. And these concepts, you have already used them probably in your daily life, but we are trying to use a physics terminology to describe those familiar concepts. And I think that's nice because it bridges away of something we already have experience with the physics. So we can change from words or language to the equations and variables. We will talk about vectors as sort of a math knowledge in the context when we do all these different kinematics quantities. So I don't want to do the math separate. We want to do it in this context. So later on, we will do more about math when we need to use them. And then we will study a very simple type of motion is simply kinematics in one dimension. Okay, the very first thing is called, the way that people wanted to study motion in a more scientific way is to draw a motion diagram. Drawing pictures and diagrams is very important for scientists, for engineers, for us to understand what is the problem. So some of you have mentioned that I can read the problem, but I have a hard time putting it down into equations. So that is where drawing a picture comes in. That's to be very handy and useful. Now, when you look, read a story, read a description, you may have a mental picture, and then we will draw it to help us to translate those words into abstract equations. So motion diagrams are easy. Simply imagine if you're trying to film a long jump, right? And you have a camera that can take snapshots in a few seconds, every few, maybe 1/10 of a second, or even take something more frequently. And you put all your frames together, right? So this is like a long jump picture. And this is like our motion diagram. We're simply just draw a picture with the location of the object at different times indicated. That's a motion diagram. Obviously, we will not be able to draw a very nice person with all the features, and physics is simply just put a little dot to represent the whole person. So imagine me walking across the room and I ask you to draw the motion diagram of that motion. Let's say I'm walking with a very steady speed. So you will draw me in this fashion. So this communicates to people a lot of important information, even though it is simple. It's showing you that I have equal intervals between the first second with the second, 2 seconds and 3 seconds, 4 seconds, and so on. You can see that I all have the same interval in my position. So that tells you something about the speed, right? You must have a constant speed. You're walking across the room. But if the motion changes, I'm sure that our motion diagram would change as well. So here is a really quick question. Now imagine instead of walking, I stroll the first half and then run the second half. How would you draw the motion diagram now? I'm going to simply set up a poll for us. I think it might be easier for us to put in our answer than the text. This is a really quick, simple question. I'm not going to send you to discuss with one another, but later on when we have a little more complicated questions, we will have a discussion in individual groups. But this one, just go ahead and vote your answer. Okay. Any last minute vote? I think I got a majority of the vote already. Any last minute vote before I close it? Okay, so let me go ahead and end the poll and then we can take a look at our results. Can you guys see the results?
Yeah.
All right, so a majority we said A, and maybe less than a third said, maybe a quarter said B. So the difference between A and B, you can see from the motion diagram, is the interval is shorter for A, right, and bigger later on. And B is quite the opposite. The intervals are longer and then shorter later on. So I'm glad that we all agree the sort of, the intervals has to change. Exactly how do you change? I think without being said, normally our convention is by looking at our time sequence from left to right. And our actual motion diagram will be more rigorous in this. We will actually indicate, okay, let's say this is 1 second or 0 second, 1 second, 2 seconds, 3 seconds, or different points. If you can take a snapshot in half a second, that would be fine too. And you can see that the intervals will represent how much distance you have changed your position over time. So as I stroll and then I run, so my intervals at first, how I change my position should be shorter or longer than later. So should I start out with the shorter intervals and then longer later on, or should I start with longer intervals or shorter later on? Which one?
Start with shorter and then longer later on.
Yes, very good. Why is that?
It's because you're not moving as fast in the beginning, so you're not like covering as much distance in each second, and then as you begin to run, you would cover more distance per second, and so the interval would be longer.
Very good, Grant. Thank you so much. So your speed will be bigger because I run. So I will run bigger distance. I have changed my position in that 1 second with much bigger distance. So A is correct. Very good. So this is just a really quick example to show what we mean by a motion diagram. Now, let's make it more official. Let's make it a little bit more like a scientific motion diagram. So to make it the motion diagram we draw to help us solve problems in physics, first of all, we model our object, whichever object you're interested in, as a point particle. So this is called a point particle model in physics, meaning that you are not concerned about the motion so much within the object itself. Let's say I'm throwing my arms around as I walk. Well, you don't care, you just care me as an entire person. How did I change my position? Where my hand is really not what you're interested in. So that's why we can model our object as a point particle. And also, what we're going to do is we have to define a coordinates, meaning that which way is positive, which way is negative. So let's say we define this one to the right is positive in the X direction, and I'm going to draw these little points as my position of my object at different time intervals. So the third, you have wanted to be label these points as a first event, a second event, a third. So you can say 0, 1, 2, 3, 4, 5, right? The first point, the second, the time equals 1 point. Sometimes we call it T1, T2. Then it may not necessarily be 1 second. It's just a particular time that you choose to look at the particle. So you have done all of these. And you can say, okay, this is my coordinates, this is my origin. This is usually easier to set your original place of the particle as the origin, because you can say initial position is simply 0, right? And if you run 2 meters, and then the next position will be in 2 meters to the right, to the positive direction or something like that. You can put your origin anywhere. But usually it is more convenient at the initial position of the particle. Okay, so you can see this is simple enough. This is simply a motion diagram. I have finished the motion diagram of some object. Okay. Now you can see there are a lot of information you can read from the motion diagram. So today our agenda is define all these concepts. So we'll start with position, and then we will read about displacement, and then we will talk about, okay, so how can you find out velocity from a motion diagram? And then we can talk about acceleration. These 4 different concepts. Okay, so first of all, position. So what is, so we all are familiar with the language position. My position is, you can tell people about your position. But if you already have a motion diagram, you can tell people, okay, the position of a point or an object is defined as a vector. Now, very importantly, this is a vector pointing from the origin to where the object is at that point. So let's say, go back to our motion diagram, say, I want to find out the position. What is the position of the object at 4? Okay, so you can say, you can here, you are right here, and start from the origin, draw a vector, meaning that we will use an arrow to represent it. So I'm going to draw an arrow right this way. Okay, so I'm going to call it position at point 4. So we use R to represent position with a subscript 4, meaning at point 4. And it's a vector, so you will see this little hook, little arrow on top of my quantity, meaning this is a vector, R4. Or if you want, you can write an arrow that is both of these are good. Okay. So this is your position. Now, I haven't explained what vector means. This is a vector. So can anybody tell us what a vector means?
It's something that both has magnitude and direction. So like maybe a strength and a direction like northeast.
Very good, very good. Thank you, Juan. It's a vector simply is a quantity has both magnitude and direction, as opposed to have something only in magnitude. Like if you say, oh, body temperature 37 degrees Celsius, and 96 Fahrenheit, whatever, then that's a magnitude, right? It doesn't really care or doesn't really make sense to put a direction on that. But the vector, you have to tell people about your direction. You can say, my position is 100 yards. Then they will ask you, well, 100 yards where? Like to the north, to the east? So you have to be able to tell people in which direction, right? So it's really, really intuitive and natural to put a direction on this quantity, and that's called the position quantity.
What if we just have a direction? Is that a scalar or is that something else?
That's a really good question. If you have a direction and magnitude usually is 1, you have a magnitude of 1, that is called a unit vector. Unit vector give you only directions. That doesn't really tell you how far it is. So a unit vector would be r hat. We use this. We don't really use it here as much, but in upper level physics, we do this all the time, is simply tell you to the east a direction with no magnitude. So R is simply, let's say 2 yards, right? To the direction of west, let's say west. So if R has simply already tell us it's west, we can multiply that by R hat. So it has a magnitude and a direction. Does that make sense? Okay, so
Yeah,
R
thank
hat
you.
indicate only a direction, but not really, but magnitude of 1 of the unit. Okay, so we have talked about vectors, and we can come up with more examples of vectors, which is the later on. All of those kinematics quantity we're going to define today, they're all vectors. Velocity, vector, acceleration, they're vectors. But there are other quantity has only a magnitude. For example, a distance, right? You say I've traveled 100 meters. Okay, we're not really concerned with direction, but simply tell me the total distance you travel. That's a magnitude. If you only want to tell people your speed, I'm going 40 miles per hour right now, that is a magnitude. You want to tell people the temperature, you don't really need a direction. All of those are a set of quantities are called scalars, right? These are all scalars as opposed to vectors. So you have two types of quantities in physics here. One is a scalar, magnitude, and you're done. Vectors, you need to add the direction. So these are the two quantities, a scalar or a vector. This has showed up in your pre-lectures already in terms of representing vectors in your coordinate systems. So for example, if you can think of vector as an arrow pointing from your origin to a point of interest here that indicate the length. So the length of the arrow showing the magnitude of the vector. So if this with a length of 5 centimeters, for example, and that is tell you what is the magnitude of a, and the direction of course is already indicated by the arrow. And sometimes we look at the vector components in the x direction or the y direction as indicated by ax or ay right here. Now you can say, you can either say I have traveled for 100 yards in, let's say, northeast, okay, northeast. You can either say directly northeast, you have traveled for 100 yards, for example. Now you can also tell people I have traveled whatever yards to the east, I traveled the same distance to the north. So you can tell people in different ways, like how much you've gone in this direction, how much you've gone in that direction. Or you can say how much I got overall in this overall direction. And that is 45 degrees in this case. Just different ways to represent direction to people. Yeah, so I have a question. Scalar only has magnitude? The answer is yes, scalar only has magnitude. Okay, so you can either tell people, I'm sorry, go ahead.
Sorry, I just wanted to know if it could be negative direction when it comes to vectors.
Oh, yes, absolutely. What I mean by negative is simply it's opposite to the direction you define to be positive. You can define however direction to be positive. So you can say, I want this to be positive. Okay, so if you have a vector that is pointing in this way, and you will call that, you will have a magnitude of -5, meaning that is in the opposite direction of where you define to be positive. Does that make sense? Okay, very good.
Yeah, thank you.
Okay, so here we are doing a little bit of a math. The reason we do a little bit of math in this context, because later on we will have to manipulate our vectors. And we need to know how to do this math before we move on. So we have defined position, right? And let's say you have multiple positions. You need to add or you need to subtract. So here, let's do a little bit of math called vector addition, meaning simply you have two vectors and you add them up. How do you do that? When they're in the same direction, it's easy. Let's say I have two directions. Oh, I have two positions. My first position is 2 feet to the positive x direction, for example, okay, positive x. And then I have another direction, which is 6 feet to the positive x. And you ask, what is my total direction? You say, what is R1 plus R2? And you quickly get the answer is 2 and 6 is 8. And it's in they're both pointing in the positive x direction. So when they're in the same direction, it's easy, right? And they're in opposite direction is also easy. Let's say you have one in this way, and then you have one opposite. The total is, let's say this is 6, this is 2 in the negative direction, and the total will be R1 plus R2. R2 is negative, so is 4 positive x. So we know how to do that when they're in the same dimension. However, sometimes a vector pointing in all kinds of different directions, how do you add them up? There are two methods. Essentially, they're the same, but the way how you operationalize is a little different. One method is called head to tail method. Is you connect this vector head to tail. So here is your vector 1, and this is your vector 2. Now, these vectors may be in different places, but you can always move them together as long as you're moving them in a parallel way, right? My 1 and 2 are different directions. But you can see I can move 2 up and down. It doesn't affect the result. I can move 2 along the 2. I can move it up or down. I can move 1 along the direction 1 and move it up and down. It doesn't really affect the result. So if I'm just moving 2 a little bit higher and move it a little bit below, I can connect them. So the tip of 1 is touching the tail of 2, right? The head of 1 is touching the tail of 2. 1 and 2 are connected here. So once you connect them like this, you complete the addition by drawing a third vector connecting from this to this point. So 1 to 2 add up to be 3. So vector 3 is vector 1 plus vector 2. So if 1 has, let's say 1 is now 5 feet and 2 is also 5 feet. Now, once they are aligned this way, this is not going to be 10 feet. Okay, the magnitude doesn't really add anymore. Okay, you can find out the magnitude later. But here, how do you simply draw the addition is head to tail method. The second method is essentially the same. It's called a parallelogram. A parallelogram is simply, okay, you have something like this, right? This line is parallel to this line is parallel to that line. So instead of connecting 1 and 2 head to tail, you connect the tail together. 1 and 2, the tail overlap, and you form sort of a parallelogram from the tip of 1 and the tip of 2. You draw 2 dashed lines, so this becomes a parallelogram. So the diagonal line of this parallelogram is going to be your third vector. Now you can see this not this different at all from the first method, because I've said you can move 2 up and down in a parallel way however you want. You can see this is 2, but this line is also 2. They're equivalent. Also, however you want to place your vector 2 is up to you. So sometimes it really just depends on your diagram of the question at hand, whether it's more convenient simply to draw from head to tail, or if you wanted to move them together, or maybe they're already moved together, right? And then maybe it's easier to do the parallelogram. So it's really up to you, whichever you prefer. So here we're going to practice using this with a couple questions doing the vector addition. Before I move on, I want to say and pause and say if there are any questions on how to add vectors together. Any questions? All right, so let's go move on to this question. So the first one, again, I don't think there's discussion needed. The second question, I'll give you a little bit of time in the breakout room. The first question is right here. Whenever you are ready, feel free to put in your answer. Whenever you're ready. All right, any last minute vote? Let's go for another 10 seconds. Okay, all right, any last minute vote? Okay, if not, let's take a look at this and I'm going to end our poll and then you can look at your results. All right, so would anybody be willing to share with us their thoughts on this? What might be one way to go about answering this question?
I kind of thought about it using the head to tail addition. So I
Okay.
noticed that the head of A was at the tail of C.
Okay.
So then drawing the line from A to C gives us B, right? So I was like, okay, so A plus C equals B. But since we have everything set to 0, if you subtract B over, it would be vector A minus vector B plus C equals 0. So that's how I did it.
Yes, very good. Thank you so much, Juan. So this is conveniently laid out in the head to tail method where A and C are the one that's been added up, right? So A plus C is a third vector. Here is our B, and you simply just manipulate B, move it to the other side, and you put a minus sign when you move it to the other side. So it's going to be this answer. So that's correct. Very good. Okay, so sometimes maybe things are not as clear. So for example, here we have a vector that is showing a minus sign. So what would be a vector that could represent vector A minus B? Okay, so I want to give you a little bit of time to discuss within your groups, but I can give you a hint. So for example, if I say A minus B is equal to a third vector C. So if I don't know how to do the minus sign, I could change this to C plus B. So you can still change this to addition, saying, okay, which one of these add up to be A? And that C is your answer you're trying to look for, right? And I'll also show you a method how to do a minus sign with the addition. So let's see. Please go ahead and capture the screen. So I don't want you to lose the problem before when you head out to your breakout rooms. You need, let's say we have maybe 4 to 5 participants per room, and we'll assign this automatically. You will have different opportunities to work with different people, and I think it's beneficial to work with different people. And I'm going to go ahead and create and then just simply accept my invitation to go to the breakout rooms. Make sure you capture this question before we go, okay? I will bring you back in a couple minutes. I'll close all rooms in a couple minutes. When you come back, please put in your vote for this question. Okay, people have already come back. Quickly put in your vote for this question, as it could be a result of your discussion with your classmates, or could be it doesn't have, you don't have to always agree with others, just whatever you think would be the right answer. All right, let's go for another 10 more seconds. Then I'll close the vote after 10 seconds. All right, any last minute vote? Okay, let me go ahead and close this. All right, so you can see that here with all the answer choices, 1, 2, 3, 4, 5, these vectors are all, they're already given in a way that their tails are emerging from one point, right? So in this case, it would be easier to use the parallelogram, because if vectors are already connected in such a way, right? So you don't have to move them around. So here we have already a hint laid out for us that we have already had a dashed line drawn for the vectors 2 and b, right? So here we want to say, okay, what is the vector we're trying to get? We have a minus b equal to 1 or 2 or 3 or 5 question mark. So which means the question mark plus b has to be a. And you can see that if I form a parallelogram from 2 and b, right? 2 and b are already touching the tails, and draw a dashed line from here, from the head of 2 that is parallel to b, this dashed line, right? And then for another dashed line that's parallel to 2, and then from where they overlap, you draw an arrow from the origin, and that's your vector a. So this is, seems like 2 and b will form such a relationship. If you form another parallelogram with other vectors 1 and b, you can see that they give you something else, right? 3 and b or 4 or 5, they all give you something else that is not a. So that means a minus b has to be 2. So there's one other method I promised you to show you how to do minus sign, is you can flip minus sign to be a negative b, right? So it's a minus b is a plus negative b. So what I mean by that is, if you have a vector a and you have a vector b, so a minus b is b flipped to the other direction, right? Simply flip direction, but the same magnitude. So you can easily draw this. So now a minus b is the new addition of a plus negative b, the new quantity that I draw here. So a and b, now you know how to do a plus b, a plus negative b, right? You draw a parallelogram, and you can see that looks like it is 2. Okay, so that's how you do vector subtraction, is you can flip the direction of your minus sign, and then that form a new quantity. So from doing that, you should already know how to do addition. You already know how to do subtraction. The very next quantity we are going to define is called displacement. Displacement simply is the change in position. For example, from here's a map of our campus from this point, and then you can go from point 0 to point 1 to point 2. In real life, you don't go directly, right? You cannot go directly. You have to drive around in the blue line. You go from 0 to 1, and you go from 1 to 2. So if we want to talk about the change of your position as you go through the campus, we will say, okay, what is the change of your position between point 0 and 2? So you have a position in 0, that is R0, which is indicated of, okay, this is your origin, this is your, at some point you're here, so that is your position at that point, R0. And then eventually you're here, and this is your another position, that is R2, right? All of those are vectors pointing from the origin to the point of interest. So R2 minus R0 will be your change of in position. For some reason, my writing is not being updated. Let me go ahead and do the share one more time, so you should be able to fix it. Sometimes it does that. Okay, so you can see, should see my writing now. So R2 minus R0 is your change of position, and that is called the displacement. Displacement. You have displaced yourself, right? You're not here anymore. You change your position. So that is delta R. So delta, this little triangle, represents the displacement, the change in position. It is also a vector, right? Because you change your position in both a magnitude and your direction. So we also define distance as a scalar. Distance is the ground covered by the actual route. So from 0 to 2, the displacement is directly aligned connecting 0 and 2. But your distance you traveled is the blue line. You can see, obviously, they don't necessarily are equal to each other. Your displacement is not your distance. Okay, so before we leave, I want us to be able to answer this question. You have an ant crawling on the floor in this half a circle, right, from here to here. So during this travel, what is the distance and what is the displacement? We know that displacement, you need a direction as well, but here I'm only asking about the magnitude. Okay, so let's quickly put in your vote before we leave. What is that distance traveled and what is the displacement traveled? Distance is the actual ground cover, so we need to know the length of this half of the circle. Displacement is simply from the starting point to the end point, you draw an arrow. That is your displacement, right? The length of that arrow is your displacement magnitude. All right, so as our votes are coming in, I can see the majority are voting for C, and they are equally voting for, about equal voting for A and B. Okay, A and B, so you can see what A is saying. A is saying they are the same. You can see in this case, this line and this line, they're not the same, right? The displacement is a arrow, a straight arrow pointing from where you are in the beginning and where you are eventually end up, your initial point, your final point. So that is a vertical line upward. So they should not all be pi r. Okay, so C. So this distance is half a circle. The entire circle is 2 pi r, so half a circle is pi r. Good, very good. And displacement is simply the diameter, right? So it's 2r as your displacement, as a way to show that these two vectors are actually different. Sorry, these two quantities are different. Distance is a scalar, displacement is a vector, and the magnitude of them are different. So C is correct. All right, so that's all we're going to do for today. We'll pick it up on Wednesday, and you should have already done your pre-lectures and bridge questions, and some of those we will discuss on Wednesday and on Fridays. All right, have a nice rest of the day. I'll see you guys on Wednesday morning.
Thank you, Professor.
Thank you, Professor.
Bye, Professor. Have a good day.
What reading should you do? I have a question here. The reading is in the achieve. Okay, is right now in achieve. That's indicated in your weekly folder. If you have trouble finding it, send me email. I can give you more directions.
You're going to be posting the slideshow, Professor?
Yeah, I plan to post the video as well, but as well as my slideshow. Yeah.
Okay, thank you.
Bye-bye.
Professor, I had a question.
Yeah, go ahead.
In regards to the vector, the clicker question, the one with the parallelogram and the dashed lines.
Yes.
So you said that we could rename vector A minus vector B as vector A plus negative vector B.
Yes. Mhm.
And you said that the negative for vector B is in the opposite direction,
Yes.
right?
Yes.
So would that be vector 3, or
Yes. It
is
looks like it is vector 3. Yeah.
because by the definition that you said earlier, it's in the exact opposite. So I was wondering if it's completely 180 degrees.
Yes. It's completely 180 degrees, and by it's a coincidence. It looks like from this diagram, the negative B is exactly 3.
Then, oh, never mind. I got it mixed up. I'm sorry.
Okay.
I was thinking that the B was the vector 2, which is actually vector C. Never mind.
Okay. Sounds good. Okay.
Thank
Thank you for the question, Jacob. See you on Wednesday.
Let's see. Thank you.
I had a question really quick.
Okay.
Regarding the same problem. So if A minus B equals vector 1, how would vector 2 kind of look like? Because I was a little bit confused on those two.
Oh, I draw, this is a crappy diagram I drew. Okay, let me correct this. I just didn't draw it very nicely. A and B is a little bit longer. It's this way. And they add up, should be like 2. Does that make sense? So A and negative B, this is negative B. So you can see how these two add up, right? So A plus negative B is 2. Does that make sense?
Okay, I get it.
Yeah.
Yeah, it's because I get confused with like when it's like the negative and when it's the positive direction. So okay, I got it.
Okay.
I got it.
Oh,
Yeah,
sounds
thank
good.
you.
Sure, of course.